Okay, so we're picking up where we left off on a previous discussion. We learned about what did we learn about? Oh my gosh, we did two theorems in the last set of notes. The factor theorem, the remainder theorem. Yeah, we learned that to figure out the remainder when you divide a polynomial by a binomial, it's just f at that value. And if f at that value is 0, then that polynomial, that binomial we divided by, is a factor. Yeah. So we're going to build on that with one more theorem, and then we're going to do some reviewing of our tools in our toolbox. So the new theorem for today is going to help us pinpoint where potential zeros are when I don't know how to factor the thing in front of me. And it's called the rational zero theorem. For future reference, I'm going to call it the RZT because I am lazy. And I don't want to have to write this over and over again. Okay, so for you guys wait till I start talking and you all make a class at the same time. For a poly f of x equals, and we know what polynomials look like, a to the n x to the nth power plus a to the n minus 1 times x to the n minus 1th power plus all the way down to a1x plus a0. That was the big formal long expression for a polynomial. Yeah. The dots in the middle mean that we could have infinitely many number of terms. All the way down from n, all the way down to 0. I'm counting by 1. So if n was 5, I would have 5, 4, 3, 2, 1. Yeah. But since I don't know what n is, I can't write all the terms out. So we do dot, dot, dot. For a poly f of x, it's, that is not how you spell possible. Possible rational zeros all have the same form, which is nice because that makes it easy to predict. Before I give you that form, we need to talk about that sentence. Well, I just said they all have the form, and then I'm going to write the form. Yeah, I did say the same. You can write the same if you want, because it is. They all have the same form. But before I write what that same form is, we need to figure out what that word in capital letters means. Rational. What does it mean for a number, because we're finding zeros, which are numbers, for a number to be rational? Does anybody remember? What's the English definition? Yeah. That's true. In English class, that is what rational means. In math class, the root of rational is ratio. What's a ratio? Think of your favorite math word that starts with an F. Fraction. Everybody loves fractions. It's their favorite part of math class. Ratios are fractions. So rational numbers are numbers that can be expressed as a fraction with integer numerators and integer denominators. They are ratios of integers. What that means is this theorem is only going to give me zeros that are rational. It's not going to give me funky numbers like pi. If I have a really weird polynomial that has a root at pi, 3.1415926, blah, 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 forever and ever, I can't find it this way. It's not a rational number. If I have complex zeros, I have roots of my polynomial that are not real numbers. I cannot find them this way. So this theorem is only going to give us some of our zeros. And notice that it says it's possible rational zeros. So we're going to get a list of numbers from this theorem. Not all of them will be zeros. But it's going to narrow down our search from the entire number line to just a couple numbers, which is really helpful. The form for these possible rational zeros is factors of a sub 0, our constant term, divided by factors of the leading coefficient a sub n. Meaning the rational zeros of my polynomial should be ratios of last term to first term. Yeah, last constant to first constant. We don't want to have to write that expression out every time we talk about it. So you're going to see your book write this as P over Q, where P are the factors of a sub 0 and Q are the factors of a sub n. Factors plural. We're going to create several fractions and identify which one of them are actual zeros. And the question is, once I've made a list of all my possible rational zeros using this form to build them, how do I check which ones are actual zeros? If I take a 0 and I plug it in for f of x, what should I get as my output? 0, yeah. Yeah, because zeros sit on the x-axis. Their y value is 0. So actual zeros will have f of p over q equal to 0. That's how we test. We build a whole list of possible fractions using the theorem, the RZT theorem, and then we use our remainder theorem to check which one gives us a remainder of 0. Yeah? If it's a short list, we can do this by hand. If it's a long list, we can use the list function on our calculator. Yeah? But either way, this part of it is calculator math. I'm just substituting in each of my possible zeros and checking which one gives me the right remainders. Yeah? Okay, so let's go down a list of how we do this, and then we're going to do a whole bunch of examples. Yeah? Okay. First, let's try one of these by itself. I think that would be good. So we're going to list the possible rational zeros of, which function did I pick? 2x cubed plus x squared minus 4x plus 1. So we're going to use the rational zero theorem, RZT. Yeah? tells us all our rational zeros should be fractions. Numerator is factors of the constant term. Denominator is factors of the leading coefficient. So let's start. What is my a sub 0? What is my a sub n? Do I still have my name color up? I do. Yes. Jackie left. That's not helpful. Brandy. What's the constant term in this polynomial? Where's my a sub 0? It is 1. Very good. It's the guy hanging out at the end that doesn't have an x attached to it. Perfect. Very good, Brandy. So a sub 0 is 1. That's nice. That's easy to find the factors of. Who else can I pick on? Aubrey. What's my a sub n? Just 2. Good. Leading term is 2x cubed. We just want the coefficient on it. Good. Perfect. My possible zeros are factors of those numbers, ratios of those factors. So let's factor them. All right, what's 2 numbers multiply to give us 1? 1 and 1, yeah? And I have to think. Plus 1 times plus 1 gives me positive 1. Minus 1 times minus 1 gives me plus 1. So when I list the factors, I pick up a plus and a minus. I get 2 factors for each of those. Plus 1 or minus 1. For 2, what 2 numbers can I multiply to get 2? 1 and 2, or 2 and 1. Good. And it's positive 1, positive 2, or negative 1, negative 2. So I pick up plus or minus 1 and plus or minus 2. Typically, when we use the RZT, we are always going to pick up a plus or minus on every factor we list. Now we have to make the list, yeah? So let's scooch you up. That is not how you spell Mr. J. Come on. And list our possible zeros. You can do this with a table. In this case, this table is very short because I only have 1 set of numerators and I have 2 sets of denominators. So reminders, this guy was my numerator. A sub 0 goes on top. This guy is my denominator. He goes on the bottom. Yeah. So for the first box, my numerator is plus or minus 1. My denominator is plus or minus 1. I'm going to get plus or minus 1. Signs match, I get plus 1. Signs are different, I get minus 1. Yay. For the bottom, my numerator is plus or minus 1. My denominator is plus or minus 2. You're right, we can't simplify, so this is just going to be plus 1/2 or minus 1/2.
So this table could be directly absolutely
The bigger those leading coefficients and constants are, the bigger this table becomes, the more potential zeros you get. We are never going to do a polynomial where those numbers get so big that this becomes a mess, right? Because we realize there's a time constraint. When you're dealing with polynomials in the real world that have much larger numbers, we use computers to do this for us. Yes, Bruno?
It can never be infinite unless the number is infinite, right?
You shouldn't have infinity as a coefficient or constant in your equation, so that should never be an issue. Yeah. They could be really, 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 really insanely big, but not infinite. Never infinite. So I have 4 zeros. I want to figure out which ones are actual zeros. So I'm going to check by evaluating my function at each of those points. I only need to do it once. The calculator can do the rest for me because I can copy and paste my entry. So let's start with f of negative 1. I know the form of my equation is 2x cubed plus x squared minus 4 times x plus 1. Yeah, I am going to type that in my calculator, and it is going to spit out a value for me. As the wonderful pre-calculus scholars that you are, I trust you also have your calculator and can check that you get the same answer I do. So I'm going to start writing my answers. For negative 1, f of negative 1, I got 4. Anybody else check? I'm a little concerned I'm not getting a nod from somebody else with a calculator. You also got 4. Thank you, Gabe. All right. Do the same thing. Now I'm going to do plus 1. Do not retype the whole expression. Save yourself the trouble. Press up and enter to copy it, and then just delete the minus signs. When you do that, what do you get? 0. Perfect. So this guy here, 1, is a 0. This guy isn't. He gave us a remainder. He doesn't divide unevenly. But yeah, x equals 1 is one of my zeros. Perfect. I'm going to give you just a minute on your calculator. I want you to calculate the other two and tell me if they are zeros.
Oh, wait. I realized.
Very good. I know they all can't be zeros because what is the degree of that polynomial? 3, and there are 4 numbers in that list. I can't have more than 3 zeros in the degree 3 polynomial. Not necessarily, because remember that my polynomial can have non-real zeros. So that's why we're checking. Where's your calculator? Put it in the backpack. Put the charger in the backpack. Leave it in the backpack. I hope so. All right. Anybody have a value for f of negative 0.5? Julie, what'd you get? 3? Does any have a value for positive 1/2 or 0.5? Probably negative 0.5 if you did it on your calculator. Yeah. Good. Are either of these two zeros? No, because they're giving me remainders. Frowny face. So I know that my polynomial has one real zero at x equals 1, and it has 2 complex or imaginary zeros somewhere else. Yeah? The question is, what do we do then? So we're going to talk about that. Yeah? We're going to look at an example to do that in just a minute. Yeah. We're going to want to talk about the whole process before we do. Before we do that, questions on the rational zero theorem. Identify the last constant, pick off the first constant, make your fractions, plug them into the equation to test them. Yeah? Tedious, but doable. Good. Okay. So, the whole process. Finding all the zeros. How do we find all the zeros? So, the first step is to do what we just did. Step one, yeah, is list all of your possible rational zeros. RZs for rational zeros, because I'm tired of writing rational zeros. And then you're going to do the second thing we did, which is once we have that list, test to find the actual rational zeros. Come on, pen. Big sentence, not big math, right? That's a calculator thing. Once we know our list, plug them into the equation. Next step is I am going to use synthetic division to remove the zeros I found in step 2. If when you did step 2, you found multiple actual zeros, you're going to do synthetic division to remove all of them. So you'll divide out one, and then you'll take that new polynomial, divide out the next. Take that new polynomial, divide out the next, until you've divided out all the rational zeros. What will be left after you've removed all of those rational zeros should be something that is a non-factorable quadratic, or it's a binomial and you get your last zero. So if you have a polynomial, an x squared that's not factorable, at the end of step 3, use the quadratic formula to find those remaining complex zeros. I just said it and couldn't remember. Quadratic formula. Before we do our examples, I want to put a little note up here next to number 1. it is possible, as we've seen from examples in class, that the entire polynomial is factorable right off the bat. So before you jump into listing all of the possible zeros, you should check if original poly is factorable. We don't want to have to use the rational zero theorem and all of that mathematical checking and synthetic division if we don't have to. So if you recognize a factoring pattern, if you notice that you can factor by grouping, that is preferable. So I'm going to make a little list here under this star of the things we should look for. If I have 4 terms, can I factor by grouping? And we saw that in our warm-up today. Right? First 2 terms together, I could pull out an x squared. Second 2 terms together, I could pull out a -6. Or no, sorry, take it -3. Words are hard today. Yeah? If it has 3 terms, can I play the x game? Yeah? Right? Factors of the first, or factors of the last that add to the middle. Can I do that? If it has 2 terms, there are 3 patterns that you should know. Difference of squares, you saw that in Math 2. Difference of cubes and sum of cubes, you saw in Math 3. Don't expect you have them memorized, but you should recognize those forms so you know that there is a formula for them that you can then go and look up, right? Because looking up that formula is going to be faster than testing for rational zeros. So for difference of squares, that's going to be, oops, sorry about that. It's going to be an x squared minus a number squared. X squared minus 9. 4x squared minus 16. 4 is a perfect square, so 4x squared is a perfect square. And we know that factors into first term minus last term times first term plus last term. You get zeros at the square root of the constant. Sum and difference of cubes are what they sound like. Difference of cubes is x cubed minus a cubed. Sum of cubes is x cubed plus a cubed. They have related formulas that look kind of similar, except the placement of the negative sign. We saw them together yesterday. So if it's a difference of cubes, it is x minus a times x squared plus ax plus a squared. If it is a sum of cubes, it is x plus a, x squared minus ax plus a squared. And I do not know what ceramics is doing today. They have been noisy all flipping day today. Oh, it would be nice if they were a little less aggressive with it. Gotcha. Reminders, I don't expect you to have this memorized. That's something you can look up. It's 2025. You have Google. On test day, you have a cheat sheet. Yeah, you should at least be able to recognize when these patterns pop up in a problem. You should go, aha, I know there's a formula for that somewhere. That part you do need to know. then go look up the formula. Yeah? Okay, let's do some examples. That's all we're doing today. That's all we're doing on Monday. Examples and practice. Examples and practice. Yeah. We're going to do one right now. Right this very second. So our example is find all of the zeros of a polynomial. We're going to do several, as many as we have time for. So first polynomial is, f of x equals 4x cubed minus 3, come on, pen, minus 3x minus 1. So first thing I'm going to do is just really quick that mental checklist. Doesn't have 4 terms, so can't factor by grouping. It's not a quadratic or something that looks like a quadratic, so I can't play the x game. And it's not got 2 terms, so it's not a sum or difference of cubes. It's not a difference of squares. So I'm going to have to go to the rational zero theorem. I can't do this by factoring. So rational zero theorem, first thing we do is look at constant term and leading coefficient. So -1, +4. And we list the factors. So we know 1 has factors of plus and minus 1. 4 has factors of what? 2 numbers that multiply to 4. 2 and 2. What else? 1 and 4. So 1, 2, and 4. And you'll typically see mathematicians list factors in order, starting with 1 and the number and then working towards the middle. We stop when we meet in the middle. Fortunately for this one, that was a short list. Good. So I'm going to list all the possible zeros, possible rational zeros. Yeah. So possible RZs. And it's factors of A0 on top, factors of AN on bottom. So all of my fractions should have a plus or minus 1, and then plus or minus 1, 2, and 4 in the bottom. So plus or minus 1 over plus or minus 1, plus or minus 1 over plus or minus 2, and plus or minus 1 over plus or minus 4. So first one, 1 over 1 is 1. So just plus or minus 1. 1 over 2 is 1/2, plus or minus 1/2. 1 over 4 is 1/4, plus or minus 1/4. So 6 possible tests. 6. And I'm going to show you a trick in just a minute because we don't want to do that manually. Yeah, we're lazy. So I'm going to scroll up and tell you how to do this on your calculator. On your calculator, you are going to press Stat, and then you are going to press Enter to select our list menu. You should end up in a list menu. L1, L2, L3, all the way over to L6, yeah? That's one way to do it. I commonly use it in my statistics classes for calculations too. Looks like this, yes? What we are going to do is we are going to put the possible zeros into list 1. So I have 6 possible zeros. I have +1 and -1. I have +1/2 and -1/2. I I have positive 1/4 and negative 1/4. So I'm just going to type on my calculator right now. We're all going to do it together. Yeah? Stat, enter. You're going to fill list 1 with those numbers. Give you just a second until I see typing stop. Okay. Next step is I want to tell the calculator to do the same thing to all of the numbers in my first list. So I'm going to move my cursor so that it's sitting right on top of that list name. So over and up. So I'm sitting at L2. And at the bottom of your screen, you should see L2 equals and then a blank space. And what I want to put here is an equation for what I want list 2 to do to the numbers in list 1. I'm putting in the formula for my function. My function is 4 times x cubed. Where did I put my x values? In my calculator, where did I put them? L1, list 1. Yeah, so 4 times list 1 cubed. How do I pull up list 1? I press second 1. As you'll notice, there's a little blue L1 above the 1 button. Yeah, second 1 pulls up the list names. Yeah. Next term is minus 3 times my x's are in list 1. Minus 1. So at the bottom of your screen, you should see this basically typed in your screen. When you have this at the bottom of your screen, you're going to press enter and something magical is going to happen. And the wow from Luis tells me that he got the answers. L2 automatically fills out with f of 1, f of negative 1, f of 1/2, f of negative 1/2. Can you give us your answers, Luis? So let me check because I haven't done it, and we'll check who's right. 4 times second 1 cubed minus 3 times second 1 minus 1. Yeah, I got what Luis got. Specifically, I got a 0 for x equals 1. I got a 0 for negative 1/2. I got something other than 0 in all of the other spots. Do I care about what those values are if they're not 0? No. Don't freaking care. What I care about is that I just found 2 actual zeros of my polynomial. I have 1 and 1. I have 1 and a half. I'm going to divide out the 1. Yeah? Because that's my next step. I found 2 zeros. Yeah? Zeros at x equals 1, x equals negative 1/2. Let's divide out the 1. We divide out the 1 with synthetic division. My polynomial, the coefficients were 4x cubed, yeah? Did I have an x squared term? No, I need a placeholder for the x squared. What was the coefficient on the x? -3, and the constant? -1. Perfect. I know that last box should be a remainder, and it should be 0 if we did this correctly. Oh, so how fast can we do synthetic division? Bring down the 4. 1 times 4 is 4. 0 plus 4 is 4. 1 times 4 is 4. 4 times is 1. 1 times 1 is 1. Gives us 0. Happy face. I see nodding. Again, happy face. Very good. So now I have the remaining polynomial of 4x squared plus 4x plus 1, which is not immediately factorable, minus, we will finish the next instinct on Monday. I'm going to push the deadline for homework 3C out a day. Do as much as you can this weekend, but you got till Tuesday at midnight to finish. We will do more practice together on Monday.